We now go to the analysis of pooled data. An independently pooled cross-section is obtained by sampling randomly from a population at different time points. For example, one can draw a random sample on wages, education, work experience from the working population every year. It is akin to doing surveys on a regular basis for the Philippines. For example, the Family Income and Expenditure Survey, or FIES, is done every 3 years. A FIES data for a particular year is a cross-section type of data. But once several FIES years are combined, it becomes a pooled cross-section data. This is only feasible if the questionnaires of the FIES are the same across all periods, or at least some variables are available on all periods. The pooled cross-section data consists of independently sampled observations in every period. This means that the observations may change from one survey period to another because of randomized sample selection. Unlike in panel data, where we can observe several cross-section observations through time, pooled cross-section data gets a snapshot of the population across time. Suppose that the same survey was conducted for 2 years, meaning the same questionnaire was used and we let the blue and red boxes represent their data rectangles. Data rectangles meaning the rows correspond to observations and columns correspond to variables. Each data rectangle is a cross-section data. When we append the two datasets together by stacking them into a single dataset, we obtain a pooled cross-section data. In a sense, we are increasing the sample size by combining several survey datasets collected across different periods. Because the observations are not collected in the same period, the data will most likely be not identically distributed. This is because the characteristics of the population may change through time, especially for an economic dataset. But the advantage of having a pooled cross-section is to increase the sample size. By pooling or combining the random samples drawn from the same population at different time periods, we get more precise estimators, and statistical tests will have more power. The analysis of independently pooled cross-section data is quite straightforward. Recall that the regression equation for the cross-section data can be expressed in matrix form as y equals x beta plus epsilon, where y is the vector containing the values of the dependent variable, x is the matrix of explanatory variables, and epsilon is the vector of error terms, one for each observation. Now suppose that the variables y and x are collected across capital T periods. And since we have several of these matrices, y1 until y capital T and x1 until x sub capital T, let's add a subscript to denote the time period when it was collected. Using the same approach as in the cross-section data, we can combine several y vectors and x matrices into one. We now write it down using the partition matrix containing the vectors y sub 1 to y sub capital T and the partition matrix of x sub 1 to x sub capital T, where y sub 1 and x sub 1 are the dependent explanatory variables collected in the first period until period capital T. We can now denote the partition matrix of y as y upper capital P, where P stands for pooled, as well as for x and epsilon. So we have an expression similar to the regression equation above. Y equals x beta plus epsilon. In this case, it has the same form, y equals x beta plus epsilon on the pooled matrices. And if we apply the same regression assumptions as before, we have the estimator x prime x inverse x prime y on the pooled data. We also have the same expression for the variance sigma squared times x prime x inverse on the pooled data. To summarize, we simply need to append several cross-section data and apply the least squares estimator in estimating a pooled cross-section regression. Pooled cross sections and panel data can be used in evaluating the impact of a certain event or policy. The data collected before and after the occurrence of an intervention can be used to determine the effect of a policy change on some economic outcomes. To capture this change in the dependent variable, we allow the intercepts to differ across periods. You may recall that adding dummy variables in the regression model leads to different intercepts per category. So we add dummy variables for the different periods, with one period selected as the base category, which is usually the earliest period. In some cases, the pattern of coefficients on the dummy variables is of interest. We can see if the dependent variable is increasing through time based on the coefficients of the dummy variables. In impact evaluation, we add a dummy variable for the group where the intervention was applied. We also add an interaction term of this intervention dummy variable with the latest period. This setup is called the difference in differences method in impact evaluation.